Dear Heavenly Father, we thank you for this day. We thank you for your creation, and we just ask that you'd help us to understand it more today, Lord. And we pray that you be glorified in whatever we do, Lord. In your name I pray, Lord Jesus. Amen. So, the other thing I had was this sheet of paper here. And so what you want to do on here is write people you'd like to, so we're working with groups of 3 for homework. So if there's 2 people you want to work with, then write it next to your name, all right? And then I will try to assign the groups from this maybe later today if I remember. So, that make sense? Okay. All right, so, and I think my copy of the book is at home. My copy of the textbook is like at home under a stack of like a lot of stuff. So, I personally, I think I have the global edition, which is like by far the cheapest way to buy the textbook. So I got like a 15th global edition for your textbook. But I'll try to get that, and then I'll suggest some practice problems from there as well. Probably I'll do that like Friday if everything goes as I hope. So just to let you know. I mean, I know the homework, there's not a lot of it, right? So you should be able to do it really well. I'm hoping. Any questions before I dive in here? All right, so we're talking about electrostatics. And so, like, generically speaking, here's the situation. We study problems where the source charges do not move. That's what makes it electrostatics. Now, on occasion, we like to do something like throw a test charge in there and let it move, all right? But the test charge is so small that the net electric field that it produces, we ignore that, all right? So we can just look at the interaction of the test charge with the source charges. So the test charge we might imagine moving because we do want to ask some questions about acceleration and velocity and stuff like that eventually. But the source charges, we're gonna keep those fixed. See, because the question of how the electric field changes from point to point dynamically is a more sophisticated question that we can't deal with at the start of the course. So we consider static situations. So here's an example. Let's suppose we put a charge Q here, we put a charge Q here, and put a charge Q here, all right? And let's suppose that this one is at like 0, comma, minus A, and this one up here is at, I don't know, let's say AA, and we'll put this guy, put this one up here at minus A, comma A. All right, that's the location of these 3 charges. And let me make them possibly different, right? Q1, Q2, Q3. All right? Then we can ask, like, if I put, a 4th charge at the origin, for example, I can ask what's the net electric force on that charge. Yeah? So what if I put a charge like right here, let's say Q. What's the net electric force on Q? Okay, that's the question. All right, so how do we do that? Well, first of all, the net force is going to be, the force from the first one plus the force from the second one plus the force from the third one, right? Because there's 3 forces, yeah? And let's see here. So for F1, what's the distance? So the Q is at the origin, right? All right, so like, let's see here. So I believe I should write Q, this is the one, Q1 over 4 pi epsilon naught. What's this distance here? What's this displacement vector? So like, so if I want to go from here to here, let's say, how about this? Yeah, I mean, we could go, what, a minus a divided by the square root of a squared plus a squared cubed. That is a vector, right? So I put a cube on the bottom so that I've got a unit vector, and of course there's a square because that's Coulomb's law. So that would give me the force of Q1 on Q. Right? And it's pointing in the right direction, right? So the electric force should be going that way, right? From 1. And then for 2, how about 2? Here, right? So like, what's this displacement vector? Plus Q2 divided by 4 pi epsilon naught. And this one, I'm going from where? I go from, that's just vertical, right? So I can just do 0a divided by, well, I guess just a squared. I'll write it out. It's 0 squared plus a squared, which is kind of dumb to write, but there it is, to the 3/2. Of course, we could just do what? Like, there's an a cubed there, right? You could simplify that. Now, last but not least, Q3 over here goes like that, right? And so force there, we'd have Q3 divided by 4 pi epsilon naught. That vector is minus AA. Obviously, my diagram's not quite right. That doesn't look like 45 degrees, does it? Probably not. The distance of the black line and the purple line is the same, right? And so let me just put myself out of my misery and just say it's 2a squared, right? It's 2a squared to the what? To the 3/2 power. Yeah? Okay, and that would be the net force on the charge Q at the origin from these 3 charges. We have to take it as a vector sum. I mean, that's what it is. Okay, so that's the general setup. Now we can do a little bit more. I can ask the question, okay, so what's the electric field at the origin? How would we figure that out? If I think about Q as a test charge now, right, I can think about this as equal to like Q times the electric field. So to find the electric field at the origin, I would simply take the expression I wrote down and divide by the little q. And that would give me the electric field at the origin. All right. Let's get a little bit more mileage out of this example. Suppose Q1 equals to Q2 equals to Q3 equals to just big Q, all right? What would the electric field at the origin be in that instance? Nope. I mean, I don't know, maybe. I'm not sure. Well, anyway, the larger point is that the coefficient in the front is the same, every one, right? Bop, 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 all the same. And we could just write those as KQ. Remember that this K is just a quick way to write 1 over 4 pi epsilon naught, right? So I can replace 1 over 4 pi epsilon naught with the K. If they're all the same Q, I can factor that out. And all I'm left with, you see, is what I've got a minus a divided by, 2a squared to the 3/2 plus 0a divided by apparently a to the 3rd, right? Because a squared to the 3/2 is a to the 3rd by, well, algebra. And then plus what? Minus a divided by 2a squared to the 3/2. So what's the deal then? Can you tell me anything about the electric field at the origin? What does it do? And does that make sense? So if all the charges are equal, right? The situation is that Q1 and Q3 are symmetrically the same distance from the origin, right? So the electric field from this is going this way, and the electric field from that's going that way. And like, let me put Q here. So like the electric field's involved. We've got the electric field from 2 like this. All right. We've got the electric field from 1 like this. Right? And we've got the electric field from 3 like this. Right? These are all in our test charge Q. So what we should expect is the horizontal parts of E1 and E3 cancel out, and we're just left with a net vertical electric field at the origin. They don't cancel out to 0 because Q2 is a distance from the origin, whereas these guys are the square root of 2 times A. So it's not quite symmetric. Yeah.
Is that Kn after the Q?
Kn?
Yep, Q1, Q2, Q3, Q, what is that?
Then.
Oh, then.
Thank you.
There we go. So, and I think you can see that here. See the x component here and the x component there. Same, equal, opposite, cancel. And all we're left with is something of the form k, q. Let's see here. Parentheses. So I got 0 in the x. And for the y, I've got like minus a over 2a squared to the 3 halves plus 1 over a squared minus a over 2a squared to the 3 halves, right? Which we could actually work out. See, both the, these are both over 1 over a squared, right? But there's a 2 to the 3 halves both places. So like, I don't know what 2 to the 3 is. What is 2 to the 3 halves, you know? Square root of 8. You're like, well, that doesn't make it better, right? So, so 2 to the 3 halves. It's about 2.82, so I've got like the reciprocal of that times 2. That's a negative minus 1. So this works out to something like, I should probably give you like a closed form expression, but this is physics, so you'll forgive me for using a decimal here. Minus 0.2929, something like that, divided by a squared. So there you go. That's the net electric field at the origin here. Can you guys think of any other interesting questions to ask for this problem? Like, what would be another interesting question you might ask if you had these 3 equal charges at these points which are given? How about this? Where would a test charge need to be in the middle so that it was in equilibrium? So that it was being pushed and pulled in a symmetric way by the 3 charges such as to just float there. Yeah. Although there's no gravity in this picture, so I'm not sure float's the right word.
Because there's a slight charge in the y direction, does that mean it's moving slightly in that direction? Or on that axis, because it's not 0?
If nothing else is holding it in place, then it would, yeah, it would be accelerating downward. That's right. To figure out the acceleration, we'd need to know the mass. So like, to figure out the acceleration of it, we'd do this. We'd be like, the force is, you know, q times e, and that would be equal to the mass times the acceleration. But I'd need to know the mass of the little q. But if I knew that, then yeah, I could figure out the acceleration due to the electric field there by the Coulomb forces of the 3 charges. How about this? Where is the electric field 0? That would give us the place where there's equilibrium. So if the electric field's pointing down here, I guess if I go maybe a little bit maybe, is it maybe a little bit up then? It would be a zero, place where it's zero? I don't know. I think a little bit up. Don't worry, I'm not going to work that out, but maybe that would be a good problem for you guys to work out. Okay, so moving on here. I would encourage you guys to read examples 3 and examples 4 in like the first PDF. Example 3, I place a charge at a point, I place another charge at a point, and then I find where should I put a charge in the middle to have static equilibrium. And when I work that, it's a one-dimensional problem. So both of the charges are on like, there's like a line. Well, if you think about this, if you have 2 charges, right? And you ask where should you put a third so that it will have 0 force, electric force, right? If you just think about the problem, where does it have to be? If I have like Q1 here, right? If I've got Q2 over here, where would I put a third charge to be in equilibrium? Yeah.
Find the net force of both, and then just take the negative of those two. The net forces.
The net force. So I'm saying there's a third charge. Where should I put it? Like, in order to have the net force on that third charge. Like if I put it here, for example. Now this is equivalent to asking the question, where is the electric field 0? See, because if the net force is 0, that's tantamount to the electric field being 0 there. Yeah.
Just like somewhere in between them?
It has to, right, it has to be somewhere in between them. Because if it's what? If it's like up off the line, the segment that connects them, or below it, then the electric force is either going to push it up, or push it down, or pull it down, or up, depending on whether they're like charges or unlike charges, right? But we always think of like test charges as being positive, just to not go crazy. But you're right, it would have to be on the line segment. Now you'd say in the middle, but that assumes something, yeah?
And to achieve equilibrium, wouldn't you need all the charges to be like the same polarity?
Yes, very much so, yes. If the charges had different polarity, then the equilibrium point would be maybe not between them, but somewhere. I mean, if this one's positive, right? And if this one's negative, it kind of depends on the values. Like if, it's a complicated question actually.
What I'm asking is if you're asking us for equilibrium, we can just assume that they're the same polarity, correct?
No, I wouldn't say that. I mean, it depends on the question. I think of them as being the same polarity usually, and I think of them as positive as a startup. I write down equations that will make sense if they're all positive. If you set the equations up right, you should just think through other cases to see if your equations still make sense. I think they will if you do it this right way, but yeah.
Would there be equilibrium at all if they're opposite charges?
Well, so what I'm trying to get at here is, if this one was large enough, there could be a large attractive force for a positive charge over here, right? And there'd be also and this could be smaller, but since your charge is closer, it could have a repulsive force. So you could have a repulsive force from the close positive charge, like suppose Q is like right here, okay? For the sake of discussion. So if this is like a small positive charge, but you're close to it, a large negative charge. So you've got electric force pulling over to this one, and it's pushing from that one, and those forces could be equal and opposite and balance out.
Okay.
But Kirk is right, the equilibrium point would not be in between these in that situation, I don't think. There could be more than one equilibrium point. We just have to work out the math. So it boils down to. And so if you look at example 3 in the notes, you'll see some of the mathematics which is involved there. All right? So I would encourage you to read that. But we're going to go on. I mean, so this is a problem we could work out Friday, for example. Okay? Something like this. I'll put that on my list of things to do. So let's talk about the electric field. From a distribution of charge. So this is page 16 in my handwritten notes. And I'll just start out with a picture to get us on the. So I draw the coordinate system, right? And so like here's Q1, here's Q2, you know, and on and on and on. Suppose I've got n of them, right? So I've got my position vector to the first one, to the second one, all the way out until I get to the nth one, right? All these position vectors. So these are the source charges. I'm supposing for the moment that we have n source charges, right? And then I want to think about what's the electric field at a test point due to these n source charges. So the test point I'll label R. So right here is the, you know, the field point. It's where we're testing the electric field at that point. Specifically, we'd be measuring, you know, the Coulomb force as a consequence of all these charges, then dividing by the test charge Q to find the electric field there. So what's the formula for this? It's just what we did in example 1, right? Except instead of having 3, we have n. And so just set this up. We want to think about the displacement vector R sub j, which is the field point minus the jth source point. All right. And notice that script r hat sub j, what it does is it points from qj to the test point q. To find the total electric field, we just add these up, all right? So the electric field at R is simply given by the summation. You guys have had Calc 2, right? So this is not new. Hey, it's only n, it's not infinity. Right? It's all good.
I won't go that far.
I mean, there's no issues of convergence here, right? I could try to work that into physics 2 if you like. I never really have managed to work in convergence divergence tests into physics 2. I could be the first. I wonder if ChatGPT could do that. Have you guys tried to solve my homework problems with ChatGPT? It won't work. I'm told by a reliable source it won't work for physics 1. Let's see here. So I'm hoping that's still true for physics 2. I really do think we should have a class that teaches how to use that wisely. I tried to talk Dr. Wang into making such a class, but he's not interested. It would be easy for him. Anyway, my brother says it writes Python code pretty well. But anyway, so what I'm doing here is I'm simply summing the Coulomb field due to each point charge and add them all up together. The principle of superposition says the net electric field at the point is due to the sum of the electric fields from all of the constituent source charges. And that's it. That's all you do. To find the net electric field, simply add the Coulomb field from each charge. It's a vector sum, right? So you have to deal with it, but that's it. Now there is another way you could write this formula, which is near and dear to my heart. You could also write it like this. I find that in practice, this is a better way to do it for actual problems because unit vectors are annoying. It's nicer to just work with vector vectors. So like, just do this instead, you know? Put the cube here. Try that again. The cubed of the jth distance, and you just put, you know, r minus rj here. Or if you want me to be explicit, we could trade that out for the length, the distance from r to rj cubed. That's just the same formula. Instead of using a unit vector, I just use, you know, a vector. But the magnitude of the electric field, of course, the magnitude of the net electric field's this thing here. Well, okay, it's complicated. I can't just say it's that thing there. There's just some. But now what? Okay, so while I've got this up here, I'd like to point out some things. Like, what happens though if instead of having a discrete collection of charge, what if instead you have a continuous distribution of charge, like a line charge or a surface charge, right? Or even a volume charge. How would you find the electric field in that situation? So in other words, what if instead of having a collection of points like that, the situation is something more like, you've got like a line of charge, right? Or maybe you've got some kind of surface of charge, like a sheet of charge. It could be flat, it could be curved, like, both. You'll find both in nature, right? You think like a basketball, put charge on the outside of it. That would be a charged surface, for instance. And then, of course, the other thing you could have is like a blob, a charged volume. Since we're in 3 dimensions, that's kind of like, that's pretty much it, right? I mean, of course, you could have combinations thereof. You could have like a line and a surface put together, something like that, right? And each one of these situations, we need a different kind of integration to deal with it. So like, for this one, we like to talk about lambda, which is the charge per unit length, so like arc length, all right? For a sheet of charge, we'll tend to talk about sigma, which is the charge per unit surface area. So ds is like a little ds, all right? Big ds is something like a little surface area element. And finally, a charged volume, you think about like a little box here, a little box with volume dV. And so the charge density is dq dV. Now, I'm sorry, the math people are idiots. They think that rho is the radius, but everyone knows that rho is the charge density, right? Rho for radius is just dumb, although it is ubiquitous and pretty much standard in every Calculus 3 course known to man. I'm sorry that they're wrong. So we like to use like R for spherical radius in physics, yeah? Okay, anyway. So these are the 3 situations. You got a line charge, you got a surface charge, you got a volume charge. And if you want to calculate the electric field due to a distribution of source charges that are over a line or surface or a volume, you have to think about this concept, you have to think about n going to infinity, right? And as n goes to infinity, what happens is this finite sum becomes a Riemann sum. It becomes an integral. An integral is just a continuous sum. You see, so the electric field for the case of a line charge would be something like you integrate over the curve of, what do? Well, you integrate, so check it out, right? So dq is what? It's lambda ds, right? So you integrate lambda at r prime. Well, let me suppress the point dependence. You integrate lambda ds, and I still got the other business. So I still got my k lambda ds over script r squared r hat. That's what you do. You integrate the linear density over the arc length. Or, over a surface, you integrate k times the surface density times the surface area element ds divided by script r squared times r hat. Or, if it's a volume charge, you integrate over the volume of k rho dv over r squared r hat. All right? Invariably at this point, somebody will say something like, but we don't know those kinds of integrals yet, so you can't make us do that. No, that's not quite how you say it, but that's the idea. But you will soon know how to do those kinds of integrals because you're taking Calculus 3. Yay! So by the end of the semester, you'll know how to do these. Although in practice, I will show you how to do these for specific examples, and then I will ask you similar examples on the test. So it won't be very mysterious. We're going to learn how to do these kind of integrals, right? Trial by fire. It's not hard. We've done some of this stuff in Physics 1. Like I did some of these sorts of things for like the gravity from like a distribution of mass. We worked a problem or two like that. But anyway, if you have a distribution of charge, we do have to do an integration to figure out the electric field. But it's not that bad. We'll figure out how to do these integrals. All right? So that said, I'm going to do another non-integral question to wrap up this part here. Let's talk about the dipole field. So suppose you've got Q1 equals to Q. You've got Q2 over here equals to minus Q, all right? And yeah, we're going to place Q1 at minus, so this one's going to be at minus A0. Let me get another color here. So Q1 is at minus A0, Q2 is at A0, I believe. So here we go. This one's at minus A0. This one over here is at A0. And we're going to calculate the electric field at 0y. So let's find the electric field at 0y due to Q1 and Q2 as shown down here. My bad. I lost track of my capitalization. All right. So we draw a point halfway between, let's see here. I should bring a ruler. I think this is the halfway point. So let's suppose this point right here is that 0y point. All right? Now, what do you guys think? What's the electric field going to look like there? Which way does it go? Down? Oh, interesting. So I think of Q as being positive, just for the sake of, specificity here. So the electric field from 1 would be like this, right? So it points away, because we think of the test charge as being positive, all right? Now, how about the electric field from 2, though? That's a negative charge, right? So it has attractive force, so the electric field here points this way, yeah. And notice that the situation is that the distance between the source point and the field point is the same for both, right? Like this distance here and this distance there, they're both what? Square root of a squared plus y squared for both of them, right? And I'm thinking of y as positive, of course, right? So what I'm saying is that the vertical components cancel out, right? It looks like the electric field should be horizontal and to the right, right? So let's work it out. So the electric field is equal to K, Q, and KQ, and let's see here. So to go from here to here, I need what? This point, again, was 0y. So I do, let's see here, I think it's going to be A, and, oh, duh, it's right here, A and Y. And I divide by a squared plus y squared to the 3/2, and then minus kq. And over here, I have minus a, and I have a, oh my bad, not a, but what? But y. And the same a squared plus y squared to the 3/2. Now, if you don't like this way, if you want to like think about an angle and use trigonometry to work this out, you can do that too. I do that in the notes. If you look at page 17, I use the angle theta and I work it out that way. But I think this is a good way. We don't need to do it two ways in class, right? So one way is enough. See what happens though? The vertical piece, there's a minus here. There's not one there, but it's otherwise the same. So this piece cancels. These pluses go together. And so what we got ourselves is a 2kqa divided by a squared plus y squared to the 3/2, comma 0. So that's the electric field. And in particular, you can see that the magnitude of the electric field, I could also write it this way, right? The electric field is equal to 2kqa divided by a squared plus y squared to the 3/2 power. And I like to use x hat. But in my notes, I tend to use I hat. Because when I wrote these notes, I was still in that system of thinking, but I prefer to use x hat these days. So I use x hat, y hat, z hat for the unit vectors in the x, y, z directions respectively. A question?
So if the point was negatively charged, would it just be the same thing but to the left?
Are you talking about this point?
Yeah, yeah.
Well, we're asking the electric field here, so we think about a positive test charge.
Okay.
If you wanted to know what the electric force would be there due to a negative charge, you just do like the force at that point, right, is the charge at the point times the electric field. So like if that was a negative charge, then it would flip this over, you know. But by convention, we think about positive test charges to figure out the electric field. That's just baked into the definition of electric field. Okay, so guys, limiting question. It's always important to think about limits. Sorry about that. I seem to be bringing limits back. This is an interesting kind of limit, though. How about this? If y is much, much greater than a, then the magnitude of the electric field is approximately what? 2q times k, well, 2kq divided by what? Notice you got an a down here, you got an a cubed down here, you've got an a squared. So if we're 1,000,000 miles away from the, oh, that feels wrong. One second. No. Hold on a second. No. Wrong. My bad. It's what? What happens? My bad. It's what?
Over y squared.
Yeah, it's more like 2k. I'm sorry. I was thinking of another example. I'm not actually thinking. I should think. So 2kq. We could leave the a up here, and then essentially it's just y to the what? Y to the third. I mean, if a is stupidly small compared to y, then the electric field is essentially like this. In other words, the magnitude of the electric field for a dipole dies off like the cube of the distance. That's different. So if you did the same problem, right, but instead of having plus and minus, you had two pluses, then we wouldn't find this kind of thing happening in the limit. All right, we're going to see why that is as we go on in here, but yeah, that's the asymptotic behavior of the electric field. It depends on the cube of the distance from the dipole. It's like, as soon as I wrote that down, I was like, that's not right. All right, let's see if we got time for one more. Maybe we do. Let's find out. Example, we'll find out soon, right? Example, what example am I on? 2, 3? I think this is at 4. This was example 3. See here, I guess I'll work over here this time. So I want to ask what's the electric field due to a line segment of charge. All right? So since it's a line segment of charge, we have to do an integration because it's a continuous distribution of charge. All right? On the flip side of things, maybe we won't have so much vector this and that to think about in this problem here. So example 4, example 5, right?
1, 2.
Oh, I can't count. Thank you. Suppose we've got a distribution of charge like so. We've got charge Q over L uniformly distributed. All right. And then I'm asking the question, what's the electric field over here at this point P? And I'm going to put the point P a distance A from the end of the rod. All right. So to calculate the electric field at this point P, due to that distribution of charge, what we do is we think about like a little bit of charge right here, a dq. And we ask, what's the electric field due to that little infinitesimal bit of charge? And we're going to say that that is at x from the endpoint, right? So context here, 0 less than or equal to x less than or equal to L. That's the setup, right? Now what's the infinitesimal electric field due to dq? Well, dE, right, is equal to k dq divided by, what's the distance from here to here? Yeah, x plus a, right? X plus a squared. That's what it is. And what direction does it go? What's the unit vector that point is? I mean, from the problem here, it's clear that it's negative x hat, right? Or if you guys like, you could put minus I hat there. If you're, I won't count you wrong for writing I hat. I'm just going to write x hat, okay? But so then what? Well, that's not, with dq, that doesn't help us that much because we need to understand how dq relates to dx. Now dx, of course, we can picture as like a little dx here, right? So here's the deal. Lambda is dq dx. Now to say that the charge distribution is uniform is to say that that ratio is still equal to q over L, right? The infinitesimal is the average if it's uniform. And so in short, we can replace this with minus k big Q dx over L x plus a squared. And of course that goes in the x hat direction, right? That's the infinitesimal electric field from that little bit of charge. And to find the net electric field, we simply take the continuous sum of this. So this tells me then that the electric field is equal to the integral, I'll pull the minus out, from 0 to L of k q dx over x plus a squared. And we can pull that x hat out because it's got no dependence on the dq. We just have to do that integral. But we can do that. That's not a hard one, right? That's what? Minus k q over L times x plus a. Actually, if I differentiate that, it gives me a minus, so absorb the minus into the integral. Evaluate that thing from 0 to L. Slap an x hat on it. You got yourself k q over L. We'll leave that out front. And that gives us 1 over L plus a minus 1 over a. X hat. And finally, finishing move here, that I'm gonna put it up here if you guys don't mind. So the electric field is k q over L. If we simplify that by algebra, make a common denominator, what does it give us? It gives us minus kq over a times a plus L. And there's, I think I lost a minus. Yeah, minus. And there's an x hat here. So don't be scared of these integrals. They don't have to be bad. We just need to set up the electric field we get from an infinitesimal charge and then add them up as appropriate to the shape. Yeah?
Wouldn't it be an L in the numerator and the denominator if you're multiplying the first, if you're multiplying?
Oh, my bad. There's no a up there at all. Oh, the L's cancel. You're right, Kirk. But there's an L over L.
Right, yeah.
So I should just have KQ. Sorry, this is what I get for not doing algebra. I'm a little bit short on time, so I was skipping steps. But all right, now let us think about the asymptotics. What happens if A is much, much greater than L? What's the electric field magnitude-wise go to? It goes to K Q over A squared, right? Well, you could put the hat on it if you like. I mean, direction KQ minus KQ over A squared x hat, right? What is that? That's the Coulomb field, right? If you just ignore the geometry here, if you just think about the line segment as a simple point charge, all at one point, right? Then, of course, it should give you the Coulomb field over here, which is just the distance from the point to the charge squared times k. I mean, the distance in the denominator, right? We have to divide by the distance squared. So, like this as a limit makes sense. Intuitively, if you're not close enough to something to like tell that there's part of the charge here and part of the charge there, very far away, it just looks like a point, you know? Like if I get far enough from any of you, you guys look like points. You know? Any questions? We're good? All right, so we'll do more of these next time.